bootstrap method in the context of regression, but more generally applies to any estimate or any statistic that you calculate. So today we're going to be talking about simple linear regression given by this equation, and we've previously seen the estimates for these statistics are given by this equation here, right here, and either of these equations here. Um, and when we saw these estimates, we were discussing the Galton data set. We were wondering if the father's height affects the son's height. So we wrangle the data to only consider sons, and then we fit a regression model to model the son's height based on the father's. And we calculated this, okay? So this gave us this equation right here, okay? Um, in order for the father's height to affect the son's height, and notice all these children are sons because we made sure the gender was male, this slope coefficient of 0.44 needed to not be 0. And we saw previously that the distribution of this coefficient, well, because it's modeled as beta 0 plus beta 1x plus random error that comes from a normal distribution with zero mean and constant variance, that in turn means that our estimator, you can prove that this estimator has a normal distribution based off of these formulas, either one of these, for it, okay? After all, that makes sense. Our data is random, so the statistics that we calculate from the data are also normal. We can also get a t-statistic if we standardize appropriately using this statistic. And we can also test the hypotheses. Specifically, we can test that the slope coefficient, beta 1, is not 0, meaning that the father's height affects the son's height. Now, what I'm going to talk about here is a way of simulating this and evaluating this claim for this hypothesis that beta 1 is not 0. And the way I'm going to do that is I'm going to calculate the distribution of beta 1 by using the data, and the method is the bootstrap method. So here's the algorithm for the bootstrap. The first step is to resample your data with replacement. Okay, so you're going to generate a new data set with replacement, and then you're going to calculate that statistic based on the formula you have. That is one bootstrap. What you're now going to do is you're going to repeat steps 1 and 2 to create the bootstrap distribution, and you're going to repeat it a set number of times. So here it's 1,000 times that we repeat it, and based on these data points generated in steps 1 and 2, we can calculate the distribution. Okay, so here, this is step 1. I resample the data, so this is just resampling the data, and this argument says allow replacement. So the same data point can be included in this bootstrap data set, that is the one that allows replacement, several times. The next thing I can do is I obtain the coefficient. So that comes from this method right here. And next, I store the coefficient right here. And then I repeat this, right, because it says for 1 in range for these number of bootstraps. Okay, I calculate the mean, that is the estimate of my slope. And then once I calculate the estimate of the slope, okay, happens to be 0.44, which is literally the same number we calculated before. That's very good, considering it's not exactly the same data. But now I can display the histogram of this estimate, and I can see that a reasonable range for this coefficient, 0.45, that's about the average, technically 0.448. But 0.45, that's right about what is the most common estimate and what you would use as your actual estimate, the average. But there's some variability to this, and there's no way that it gets really below zero point 0.3. It'd be very unlikely. It doesn't get any bigger than like zero point 0.6. So that tells you like what's a reasonable range for the estimate. Okay, so using this, I can calculate uh, what is the most likely value of this coefficient, what's the most probable, so I can calculate like a 90% confidence interval, or I can look at the histogram to understand like the error for these estimates. But I'd see that 0 is not a reasonable estimate, that it almost certainly has to be above zero point 0.3, and absolutely it's above 0. So this coefficient, there's no way, according to this histogram, that the coefficient of father's height could be 0. It has to affect the son's height. Okay? And if we look at this histogram, it reinforces these distributions, the fact that it's normally distributed. Okay? So this very much resembles a normal distribution. And so this is one way of numerically validating this distribution that we know from theory. Okay, and that was just using the bootstrap sample. Now I'd like to point out I could do this for any statistic. I could do this for the intercept. I could do this for the AIC, the BIC, the R squared, the F statistic, anything that's calculated with a formula and from the data. I can use the bootstrap process. Okay, thank you very much.